4.1 Inverse functions. We start with this concept called one-to-one. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. All right? One-to-one function. You can see right here in this diagram, this one is the one that causes a problem. Okay? You've got to go back and you've got to remember this definition. Each x value corresponds to only one y value. So when x equals 2 goes to 7 and x equals 3 also goes to 7, that's going to be a problem making this not one-to-one. Over in the other one, we don't run into that issue because each x value corresponds to only one y value. I want you to keep going back to that definition. Each x value in this domain goes to only one y value in this range, so this one is one-to-one. Now, the reason it's going to be important to think about one-to-oneness is a function has to be one-to-one in order to have an inverse. So this lesson is going to be about inverses. It's got to be one-to-one in order to have an inverse. So they give you this way to test and see if something is one-to-one. Now, I don't really love this because there is an easier way, but they're giving you a test, a way to test if it's one-to-one. So it says, if you've got A not equal to B, that implies that f of A does not equal f of B. Honestly, the contrapositive is probably more useful to us. Contrapositive, go back to geometry, if you reverse the statement and negate it, looks like this. These two statements actually say the same thing, okay? And I think the one in blue here is a little bit more useful. They're saying that if we know that f of A equals f of B, then we can assume that A equals B, all right? So this is a test. This is a test for is this function one-to-one, and it's not, honestly, it's not the best test. So example 1 says decide whether each function is one-to-one. And so what we're going to do is we're going to go back here and look at this blue box. We're going to say f of A equals f of B, and then we're going to see whether or not A equals B. So let's just say that f of A, okay, f of A means plug in A, you'd have negative 3A plus 7. And then let's do f of B. F of B equals negative 3B plus 7. So what that statement says is it says that let's just assume that we've got f of A equal to f of B. F of A was negative 3A plus 7, and f of B was negative 3B plus 7. So we assume that those two things are equal. And let's see what happens. Well, we're gonna try to isolate a variable. So let's subtract 7, and let's divide by negative 3. It says A equals B. Okay, so remember what that theorem said a second ago. FA equal FB implies A equals B. Well, that's exactly what we just came up with. So when we had FA equal to FB, then we ended up getting down to A equals B right here. And so when we see that, that's how I would know that f of x is one-to-one. Part B, we could do the same thing, or actually it's going to be easier on this one. to use the statement in red. A not equal to B implies f of A does not equal f of B. So what I'm trying to show is something like two numbers go to the same y value. All right, remember what 1 to 1 is. Each x goes to exactly one y. So what I'm going to do here is I'm going to try something like f of 7. And you don't have to pick 7. You can pick whatever number you want. If I plug in 7, I have 49 minus 7 squared. That's square root of that. Square root of 49 minus 49. Square root of 0, which is 0. Okay? So when I plug in 7, I get 0. Now I'm going to try a different number. If I try negative 7, square root of 49 minus negative 7 squared, be careful with your parentheses. When you square that, you're going to get square root of 49 minus 49. Square root of 0 equals 0. So what we just showed is that two different x numbers both go to 0. That's not 1 to 1. Okay? So remember what the statement said. A does not equal B implies f of A does not equal f of B. Okay? That didn't work. That broke down. Okay? This f is not 1 to 1. I think it's easier to see in this little diagram over here. F is not 1 to 1. So honestly, guys, the horizontal line test, this is another test. I gave you a test before. This test is much, much better. Okay, this test is a better test for figuring out if something is 1 to 1. A function is 1 to 1 if every horizontal line intersects the graph of the function at most once. So you might remember the vertical line test, but go back and look at what this function looks like. Example 1a. If I was going to graph this, who can tell me what f of x equals negative 3x plus 7 looks like? That's a line. Very good. Specifically, the negative 3 tells me it goes downhill. It's going to be a line, looks something like that. But the horizontal line test does this. Horizontal line. Any horizontal line you draw only hits one time. Okay? If it only hits one time, it's 1 to 1. Okay? Now, you probably don't know what the other graph looks like. Not quite a parabola. It's the top half of a circle of radius 7. Okay? That's what it is. It's the top half of a circle of radius 7. So you should be able to see a horizontal line test is going to hit in more than one spot. Think about what the vertical line test told us a year or so ago. Okay? When it hits more than once, it's not 1 to 1. Okay? So I like the horizontal line test much, much better than the other test. So real quickly, determine whether each graph is 1 to 1. Is this graph 1 to 1? This one's 1 to 1. Is this graph 1 to 1? Not 1 to 1. Much quicker than the other test. In general, a graph that's either increasing or decreasing on its entire domain must be 1 to 1. Okay? So even if you don't see the actual graph, but if you just know that it's increasing the whole time, if you know it's increasing the whole time or decreasing the whole time, you can say that it's 1 to 1. So to sum up, we did these two tests in example 1. I like the horizontal test a little bit better, and then also if you know it's increasing or decreasing over the whole domain, those are 4 different ways to tell if it's 1 to 1.